Okay, so for 3.4, we're going to be talking about carrying capacity of a population. And a carrying capacity is the maximum number of individuals in a population that an ecosystem can support. And the number of individuals that can survive are all going to be based on different limiting resources. So, limiting resources would include things like habitat space, food, water availability, all of those different resources that organisms need to survive. So, figure one is theoretical. Figure two is actually much more realistic, but let's go through and explain what is going on in these two graphs that we're looking at. So, figure one shows exponential growth early on, and then as we start to reach the carrying capacity of a particular ecosystem, the amount of growth will begin to slow down, which is what we're seeing here. Excuse me, until it balances off where the growth rate actually falls to zero. And again, this is the carrying capacity. So this is the amount of food, this is the amount of water, this is the amount of living space, this is the amount of all the resources that are needed to survive. And we can see here that we generally call this an S-shaped curve. Um, this is unrealistic because the population just doesn't stay at, oops, let me go back. The population doesn't just stay at this even balance. It actually does this. Okay, so the population grows exponentially and then it reaches carrying capacity. It exceeds carrying capacity generally. And then some of the organisms don't survive because they run out of resources or there's a lot of competition and they don't overcome that competition. So there's a die-off event, and then they start to grow again because there's some resources available, and then this competition leads to die-off, and then we continue this cycle of overshoot and die-off, overshoot and die-off. So the theoretical piece, why we even look at this figure one right here when we're talking about carrying capacity, is because if we were to look at the average survivability of this population, it's going to balance out to this zero growth once it reaches the carrying capacity. Okay. Other things to know about this is that carrying capacity is represented as a K. And let me stop my webcam here to see if there's anything we missed. No, I think we covered everything that's on there. I was kind of blocking some of the text. But I think that's pretty much what you need to know. We've got an S-shaped curve, the carrying capacity represented as K. The actual growth of the population averages out to be zero, but realistically, we see this overshoot and this die off over time. Okay, so this just sort of reinforces everything that I just said. So it might be a good idea to pause the video here and write some of this down. But just to kind of reiterate here, we've got the definition of carrying capacity, some of those resources that limit carrying capacity. It gives you a definition for overshoot. And one example of that would be deer breeding in the fall. They tend to give birth all at once in spring. So there's a sudden overshoot in the population in spring and early summer for deer population. But then we'll see that the population, those that are weak, sick, whatever, some individuals just run out of food supply, they'll die off. And then we go down back below the carrying capacity, and then we can creep back up again for the next year. So we tend to see this overshoot in this deer population. Same thing with rabbits. The exact same thing happens with rabbits. So the consequence of overshoot is that we end up with what we call resource depletion. So overgrazing in deer, rabbit, etc. And then we have this die-off, which is a sharp decrease in the population. And so many deer do end up starving. It's a sad thing. And same thing with rabbits, but we just don't, they have way too many babies for the available resources in their area. And especially that's true when we have habitat destruction because we're building more and more homes. Okay, so here's another kind of popular, famous die-off that occurred. There were reindeer in St. Paul Island. There were 25 that were introduced in 1910. The growth was very gradual if we're reading this graph. So we have 1910 as the start date. There's gradual growth. And then when we get, between the years of 10 and 30, very gradual growth, but then we hit year 1930 and there's an exponential growth that you can see here. So you get this nice J curve that we tend to see with exponential growth. but then the carrying capacity is overshot. So they just really went over the carrying capacity, which if I were to guess would probably be somewhere around 1,600 deer. Kind of hard to tell because we don't see that overshoot and die off continuously. So where we can get kind of that average. And in this case, the population just completely depleted. And so real populations don't always fluctuate around that carrying capacity. If the resource depletion is severe enough, so they way overshot the carrying capacity because they weren't hunted, there was no natural predators of these organisms. So they just ate up everything. Then they ended up having a population crash. And so by 1950, reindeer were extinct on St. Paul Island. So that's a more realistic example of what can happen when we try to introduce things ineffectively. And so that is just something to remember, and make sure you're just reading your graphs. AP likes to present a lot of graphs when we're showing carrying capacity and kind of have you figure out what the carrying capacity would be, or sometimes even data tables. So just really look at those numbers so you can try to make sense of what's happening. Okay, something that goes along with carrying capacity are predator prey models. And so we can see here, because the predators are so dependent on the prey, which is their main resource, that's their food source, main food source. And so we'll see that one actually responds to the other. So in this case, it's the hare population in purple that has to increase first. And then just maybe a year or so later, then the lynx population sort of follows. And so then, the hare kind of overreach or overshoot their carrying capacity. So they start to drop. What happens then? Now we're running out of a food source for the lynx, which is a type of cat. And so then the lynx, again, a couple months later that or a year, then the lynx population also declines. And so it actually drops out because of the severe resource depletion of the hares. And then after the hare population starts to increase again, we see some nice exponential growth here where we overshoot the population, die off. Okay. And then a year or so later, the lynx kind of, the lynx kind of follows. Okay. So, I think it's really important to note that they love to put a predator prey graph and then say which is the predator, which is the prey, who responds to who, and it's always the predator that's going to respond to the amount of prey. When the prey overshoot their carrying capacity, they drop off, and then the predators will follow. And then when there's enough resources again, they start to increase significantly, die off, increase significantly, die off. This is a very cyclical thing that happens between predators and prey. Okay, so for today's practice FRQ, and this is a great example of an AP type question that you would see on a test. It says, explain the impact that the canine virus had on the moose population based on this graph. So moose are going to be the prey. The canines, the wolves are going to be the predators. So explain that impact. And if you have any questions, make sure you're talking to me in class. And next time we're going to be talking about population growth and resource availability. That's it for today. See you guys next time.